Right? Now we are ready to prove the one remaining theorem about L-intersecting families, namely the theorem about the uniform modular uniform family of sets where the intersections have a certain size also in the modular something. Right? So here's the theorem by Alon, Babai, and Suzuki in 1991. So P is a prime, and L is a subset of integers from 0 to P minus 1 of size S, and we assume a certain condition S plus K is less than most N. And if you have a family of subsets such that each member has size K modulo P, and intersection of distinct members have size something in this set L modulo P, and the K is not in L, then this family has at most N choose S members. Now let me first recall the proof for, the proof that we did for Wilson, Rayleigh, Chaudhuri, and Wilson's theorem, 1975. So if we don't have a modular condition, then we had a proof, right? And the way we did it was to make polynomials, and we add more polynomials, and then prove that they are linearly independent. Right? That's how we prove this theorem 2. So we're gonna use similar idea. Okay, so let me show you the proof of theorem 2 here on the left hand side. Right? I'm gonna copy many things. So let's say f is a1 up to am, and each of ai is congruent to k modulo p, right? And assume, we can assume that k is less than p, right? And yeah, so k is less than p and is 0. Now do the same thing. So let ai be the now instead of real field, I use this fp, so field of size p to the n be the characteristic vector. Of ai, right? So the coordinate is 0 if it contains the corresponding integer, and 1 if it contains corresponding integer, and 0 otherwise, right? And let's say L is L1, L2 up to Ls. All right. And then we define, like before, fi of x to be the product from 1 up to s, and x dot ai minus lj for x in fp to the n. Right? It's the same. And we also reduce, right? So let fi tilde be the multilinear polynomial obtained from fi by repeatedly replacing xj squared to xj. So the whole purpose is to make sure that fi tilde x is equal to fi x when x is in 0, 0, 1 vector. Then they are linearly independent, but we need more, right? So we again construct for every subset I of 1 up to n with cardinality less than s, yeah. So define gi. Again, looks like same. Yeah, so I'm copying from the left hand side. Yeah, this is my polynomial gi, and this is for x in this. All right, and that gi tilde be again be the multilinear. Why is it multilinear? Because whenever you have a square term, you reduce it by linear term. So multilinear polynomial obtained from gi by repeatedly reducing xj squared to xj. All right. Now again, gi tilde x is gi x when x is 0, 1 to the n. Now again, we claim same thing. F1 up to Fm tilde and gi tilde for all I subsets of size and most, less than s, are linearly independent. Right? Wait, you may say, so far everything is the same. I just copied from left hand side to the right hand side, except the field has been changed. Instead of using real field, I'm using this finite field. So if true, right? If true, then again, m plus n to 0, n to 1, n to s minus is going to be less than or equal to the dimension of the vector space of multilinear polynomials of degree at most s, right? So that is sum of n choose I from 0 to s, right? So that's the dimension of, okay, everything should be clear now, right? Because these are linear, so the size of the linearly independent vectors will be at most the dimension of the whole space. And this implies that m is at most n choose s, right? So it's enough to prove this claim. So suppose that alpha I fi tilde plus beta I f gi, right? Suppose this is true for all x. All right. Now, what do we know? Take x to be ai. What's going to happen? Are you happy with this modular p? Anyway, doesn't matter. Right? This whole equation is over the finite field of size p. All right. If x is ai, then gi tilde x is gi x. No, let's not say ai aj. But size of set AJ is congruent to K modulo P. So this is 0. Right? So what's left is sum of n, right? So if fi tilde aj is actually equal to fi aj, right? And that is non-zero or 0, right? So if it's non-zero, if I is equal to j and 0 otherwise. That's the whole setup. So therefore, alpha j, fj tilde aj will be 0 modulo p. So aj is 0 modulo p. So no, not aj, alpha j. Right? So that proves that all the alphas are 0. Now what's left is the beta. Right? So for beta, so suppose that there is I such that beta I is non-zero, then choose a minimal subset I0 such that beta I0 is non-zero. Right? So among all sets I, choose the one that is minimal and yet the beta is non-zero. And let x star be the characteristic vector. Of I0. So that means x star is 1, the coordinate for x star. So x star is x star is a vector in f to the p to the n. So this x star is some vector where it's 1 if it's in I0 and 0 not in I0, right? So the i's coordinate is 1 if I is in I0, j's coordinate is 0 if j is not in I0, right? Now what's going to happen, right? So we want to look at the evaluation. So gi, what is gi tilde x star? I know that size of I0 is strictly less than k, right? So gi x0, no, gi. Now let's see, I think it's the same proof. Right, so gi tilde, by definition, these are the product of, yeah, so here's the definition. So this term will be non-zero because sum of xi to coordinate will be less than k. And since we chose k to be a number less than p, so there's this number. Yeah, I would. Right. Yeah. But anyway, if there's, yeah, let's see. If I is not subset of I0, if I is a proper subset of I0, then oh, right. So in this case, beta I, okay, let me say it again. So beta is going to be 0 if I is a proper subset of I0. Yeah, that's right. And that's because of the choice of I0. Otherwise, we could have replaced it. And if I is a superset of I0, then what's going to happen? Then that means I'm multiplying somebody over here on the left hand side. So we have some coordinate which we will multiply, and I0 doesn't contain that. So that means that coordinate value will be 0. So gi tilde x star will be 0 modulo p. I don't need a modulo p anyway, it's equal to 0. Right? So if I is a superset of I0, then this is 0. And what else? Oh, actually this is not a, I should say, if, yeah, the better way is, if I is not a subset of I0, then this is 0, right? If I contains any element not in I0, then it's 0. Right, so what do we know then? Then we know that for all subset of I0, beta 0 times gi tilde x star is 0 modulo p. All right. Yes. But for any proper subset, beta 0 is, no, not beta 0, beta I. But for any proper subset of, if I is a proper subset, beta I is 0, so that means beta I0 gi tilde x star is 0 modulo p. And so beta I0 times, so gi tilde, in gi, so gi tilde is what? Oops. Gi tilde x star is equal to gi 0 x star, which is equal to size of a size of I0 minus k, right? And so therefore what we know is beta I0 times size of I0 minus k is 0 modulo p, right? And I know that beta I0 is non-zero, so I0 is k modulo p. Now that's the difference, right? The previously we didn't have such an analysis. And I know that k is less than p, right? And I0 is less than s, but s is less than or equal to p, right? So I0 is equal to k. Right? So whenever, yeah, so what this tells us is that if beta I0 is non-zero, and if I0 is minimal, then that set must have cardinality equal to k. All right. Now we want to apply Mavericks inversion. And we assume that beta I is 0 if I is at least s. right? So we didn't define, previously we didn't define these coefficients, but now we're gonna define it to be 0 if size of I is at least S. Now, here's a subclaim. If cardinality of J is not equal to K modulo P, then the sum of these beta T, let's say T is a subset of J, this is not, this is equal to 0 modulo P. Why? Again, let X star be the characteristic vector of J, and this, I mean, in FB to the N, right? And then we know that 0 is equal to the sum of beta I, Gi tilde X star, right? And this is like size of J minus K. Oh, and this is equal to beta I, and then size of J, well, beta I and Gi and X star, and that is equal to beta I times size of J minus K times the product of these things, but that product will only survive when I is a subset of J, right? So that's modulo P. And since size of J is not equal to K modulo P, this implies that beta I is 0. Modulo P. All right. Now that proved the subclaim. Now let J0 be a subset of 1 up to N such that the right, and oh, 1 up to N or 1 up to S, maybe. No, it's 1 up to N, such that size of J0 is K plus S, and I0, it contains J0. So why can I choose that? Well, this is where we use the fact that K plus S is the most N. So we had this condition, remember? So I choose arbitrary set. Choose some set containing I0, but size is K plus S. All right, and since size of J0 is less than P plus K, right? Or in other words, K plus P. Now we know that J0 is not congruent to K modulo P, right? And then by the previous claim, beta t, if you sum up over all so for all j subset of I, beta t is going to be 0 modulo p for all j, which is subset of j0, where j is not equal to k. Right. Oh, yeah. So, right. Maybe I remove this. Yeah. So this is 0. There's a p and twice p. There's somewhere there's a k and k. There could be. I mean, yeah. K is less than p. So p plus k is here. I know that j0 is in this interval. Then the only way it could be congruent to k is this number. So that's why this is here. Right? So whenever size of j is not equal to k, then we know that sum of this beta value is 0. Now, this is where we're going to use the Mavericks inversion formula. Right? Recall the Mavericks inversion formula. But now we're going to use for set, right? So what we're going to use is a version where right, so in the left hand side you see this thing. Now I'm gonna think that P is a post set. Right, so what would be a better setting? Okay, I'm gonna write this way. So S2 T2. So this is like B, right? So I have set B, and inside I have subset A, all right, and B minus A. And you can think of this part making a post set P, and this part making partially ordered set Q. And then whenever we have a subset here, then the union is given by, right? So union gives us some function. So what I do is imagine that I have a function, right? So let's say f is a function defined on subsets of B to some field f, and g is a function that gx is defined as a sum over all subsets of x and f of x, right? And then if you use these formulations, sum over all subsets of second poset, so T2. So this is going to be, this red part is going to be T2, this red part is going to be T1. So for all subsets of T2, so that means I am fixing A side. So I contain A, so it's in between A and B, so for all subsets of that. And then I apply Möbius function, so the mu S2 T2, that's going to be minus 1 to the size of B minus size of A, right? That's Möbius function for sets. And then the function is G of A. 네. T, yeah, G of T. 알겠습니다. 제가 도와드릴 일이 있나요? 아니요. Okay, so that's equal to the sum over all Now on the right hand side it's T1, so that's you contain B minus A and B, and it's f of t. So that's the consequence for the lemma in the Möbius inversion formula, right? So this is the formulation that we're going to use. All right. Now how are we going to use that? So A is we take A to be I0 and B to be J0, right? Remember, J0 is here and I0 is there. And then we will obtain the following, right? So I0 and T. All right. If you apply that, then what we get is minus 1 to the B minus A. Right? I mean, what's the point? What's the point? Right. Right. And then here we use this formula, right? So sum of the beta I need a letter U, let's say U is a subset of T, and that's equal to J0 minus I0 subset T and J0 and beta beta T. All right, so we obtain this. Now this thing, I know that this is 0 unless T has cardinality K. But I0 has, right? So this whole thing is 0 unless this T has cardinality K, and size of I0 is less than right. Cardinality of I0 was, yeah, so remember we already knew that cardinality of I0 is exactly K. So on the right hand side, the only way where this term could be non-zero is when this whole thing is equal to, oh, it's not B minus A, it's actually J0 minus T. So J0 minus I0 times beta I0. That's the only term on the left hand side. And right hand side is beta T. Right? And I know that this is non-zero. So beta, yeah. And what happens with this term? So let's look at the size of J0 minus I0, right? The size, what is the size of that? So J0 has size, we chose J0 has size K plus S. And this has size K, so that has size S. Right? And so these are sets of size S to s plus k, right? And I know that the k, yeah, now I'm confused. Right, where's the diagram? Yeah, so k is here, k is some number there, and k plus s is less than n. Do I know that k is less than s? Let's look at the conditions. Right, k is less than p, and yeah, so here's a set of size s. So this is 0, p, twice p, and s is somewhere here, right? And oh, never mind. Nothing to worry, because remember, this is size, and we already assume that beta t is 0 whenever t has size at least s, right? Because these are coefficients. The coefficients, there were no coefficients for sets of size at least s, so we don't need that. So we end up having the right hand side to be 0, right? So whenever t is bigger than j0 minus i0 and j0. So that's a contradiction. All right, so this proves the claim. All right, so where is it? This proves the claim that these polynomials are linearly independent, right? So therefore, that proves the whole thing, the Allen-Suzuki theorem. Right? Okay, yeah, that's it.